In this video, we're gonna give some motivation for homology. First, we're gonna talk about some historical motivations, and then we'll discuss some practical motivations. Now, historical here is a misnomer because our goal is not to be historically accurate. Our goal is to present a nice narrative. So let's start our story. Now, once upon a time, mathematicians were looking at vector fields on regions in the plane. Let's assume for the rest of this video that everything is nice, so all vector fields are continuous, all functions are continuous, and so on. Now, they have many questions about such vector fields, among which is the question, how do we tell whether or not this is a conservative vector field? Or equivalently, how do we tell whether or not it has a potential function, i.e., is it the gradient vector field of some function f? Actually, this fits into a more general family of questions. For example, given a continuous function on some interval in R, we can ask if there exists a function f such that g is the derivative of f. Or given a vector field in R3, we can ask whether or not it's the curl of some vector field. Or given some function f on R3, we can ask whether or not it's the divergence of some vector field, and so on. If you know differential forms, then you see that all of these questions are just asking, given a differential form tau, how do we know whether or not it's gonna be the exterior derivative of some form omega? In other words, which differential form is exact? Now, one approach to this is via the Derived Homology, and for that you can look at our playlist on manifold. But this is algebraic topology, so we want to talk about how the topology of the region D creates an obstruction to this. Now, can you guess which topological invariant is gonna measure the obstruction to this? Well, because of the title of this video, it must be homology, which we can think of as an invariant that captures n-dimensional holes. In what follows, we're gonna see how these holes have anything to do with solving this problem. Now, for illustration, let's just focus on the dimension 2 case. So the rough idea is as follows. We'll show that V is conservative on a region D if and only if the integral of V along any closed curve C in D is 0. In particular, the obstruction to V being conservative on D are exactly the obstruction to integral of V along these curves here being 0. And the obstruction to that are exactly the one-dimensional holes in D. That is because the integral of V along any closed curve that does not contain hole inside it must be 0. So the troublemakers must be the curves that contain a hole. Now, but what exactly are holes? Well, we can think of them as closed curve that does not bound any surface. So a way to measure the obstruction to V being conservative on this region D would be to look at the quotient of the set of closed curve by the set of boundary of surfaces. And this is gonna be kinda like the definition of the one homology group of D. Well, except that we actually want this to be a group. So we have to groupify this, i.e. look at the free abelian group generated by these. Now similarly, in higher dimension, the obstruction to the same problem are the higher dimensional holes. So for example, here we drew the case of R3. Now in R3, the two-dimensional holes are exactly closed surfaces that do not bound any three-dimensional thingy. And similarly, we can look at the quotient of closed surfaces by those that have boundaries, and that should give us information about obstruction to solve this problem. Once we groupify that, once we turn that into a group, we get the second homology. And we can keep repeating the same idea for higher dimension. Now, that was our TLDW, and if you got it, you could leave now, since we will not be using the rest of this discussion for the course. However, if you're interested in details, if you want to know why we have these equivalent, then keep calm and watch on. All of these comes from Stoke's theorem, which says that the integral of a differential form omega along the boundary of a region D is equal to the integral of d omega, the exterior derivative of omega, on D. You have seen a version of this before, in the case when D is an interval. Stoke's theorem in that case is just the fundamental theorem of calculus. Because if we give this orientation, then the boundary of this interval is just a minus b, and so Stoke's theorem says that the integral of the derivative of f over this interval must be equal to fb minus fa. Now, for establishing these two equivalences, we are gonna use two other instances of Stoke's theorem. For that, we're gonna need Stoke's theorem for the case when omega is a zero form on the plane. That will give us the fundamental theorem of line integrals, and then we'll also need to use Stoke's theorem for the case when omega is a one form, and that will give us Green's theorem. Now, before diving into this, we want to make a quick remark that we can view a vector field as a one form. Or more precisely, I should say that there is a bijection between vector fields on Rn and one forms on Rn. So when I write integral of a vector field like this, I actually mean the integral of the corresponding one form. But the exact definition of these doesn't matter. Alright, so now let's dive into this first equivalent. We want to show that V is conservative on D if and only if the integral of V along any closed curve on D is going to be 0. So let's first show this direction. Well, if V is, say, the gradient of some f, then integral of V along any closed curve by this formula is just gonna be fa minus fa, which is 0. Now let's look at the other direction. Suppose the integral of V along any closed curve in D is 0. Then we can construct a potential function f for V as follows. Imitating the construction of antiderivatives in one-dimensional calculus, we can just define this f at any point xy to be the integral of V from a fixed point A to xy. And this is well defined because if I take two paths from A to xy, then if I reverse one of them and combine them together, I get a closed curve. So the integral of V along this closed curve must be 0 by hypothesis, and thus the integral of V along these two paths must be the same. So this integral does not depend on the choice of path, it only depends on the endpoints. Thus it is well defined. Thus we have established that obstructions to V being conservative on D are the same as obstructions to integral of V vanishing along closed curve in D. Now next we want to show that obstruction to V vanishing along closed curve in D are given by the holes of D. Another way of saying it is that we'll show that if C does not contain a hole in its interior, then the integral of V along C is gonna be 0. Note that this condition is only for good V, those that satisfy a necessary condition for being conservative. What is a necessary condition that we're talking about? Well, observe that if V is conservative, then that means that the components of V are just partials of F. And so in particular, by Fubini's theorem, we have that P, the partial derivative of P with respect to Y, must be equal to partial derivative of Q with respect to X. So we are only going to look at those vector fields that satisfy this necessary condition for being conservative, i.e. those with components PQ such that PY is equal to QX. Now to see this implication, we need another version of Stoke's theorem. This is for in the case when omega is this vector field V, i.e. is a one form. In that case, we get Green's theorem. So here, if we have any region B that lies inside our original domain D, then Green's theorem says that the integral of V along the boundary of B is gonna be equal to the integral of this expression on B. In particular, observe that if V is good, i.e. for V we have this equality of the partial, then this term immediately vanishes. So we get that integral of V along any boundary is gonna be 0. Thus, if C is the boundary of a region like this with no hole inside, then integral of V along C must be 0. Now let's see what happens when C contains some holes. In that case, the integral of V along the boundary of B, this region B, is still 0, but the boundary of B now is no longer C. It's gonna be C minus C1 minus C2 minus C3 if we fix an orientation. And so the obstruction to the integral of v along c being 0 are exactly these integrals, the integrals along the holes. Thus we see that the obstruction to v being conservative on D are exactly the one-dimensional holes in D. And what are one-dimensional holes exactly? Well, these such as closed curves that do not bound any surface. Thus we see that we could measure the failure, the extent to which V failed to be a conservative vector field, by looking at the quotient of the closed curves by those that are boundary of surfaces. This leads to the definition of the first homology group. Though we lie a little bit because we need this to be a group, so we have to groupify this somehow. In other words, we need to look at the free abelian group generated by this. Similarly, in R3, the obstruction to a vector field F being a curl of some vector field are exactly the two-dimensional holes. And these are just closed surfaces that do not bound any three-dimensional thingy. So, we could also look at the quotient of the group generated by closed surfaces modeled by those that bound a three-dimensional thingy. And that's gonna be the second homology group. We can just generalize this to n dimension and get the nth homology group. So that's the historical motivation of homology. It helps us measure the extent to which a differential form fails to be exact using the topology of the underlying space. Next, we're gonna look at some practical motivations for homology.